sir. Good morning, classmates. Let me continue the discussion about the cratered worlds. So, in this section, we'll be focusing on the origin of the moon. But before we start, let me present to you our learning objectives. So, by the end of this section, you will be able to describe the top 3 hypotheses of the formation of the moon and summarize the current giant impact concept of how the moon formed. So let's have a short review about the moon first. So our moon is geologically dead, no permanent atmosphere, no magnetic field, average density of only 3.3 grams per centimeter cube, almost 1/8th mass of the Earth, made almost entirely of silicate rock, and the prominent crater are those named for Plato, Copernicus, Tycho, and Kepler. Now let's begin to our main discussion, and we'll begin with the ideas for the origin of the moon. So we have here the 3 general hypotheses on how the moon formed. The first hypothesis is the fission theory, which states that the moon was one part of Earth but somehow separated from its early in their history. It suggests that the Earth was spinning so fast around its axis and a small part of it broke away and started to revolve in our planet. The second theory is the sister theory, which states that the moon formed together but independent of Earth, as we believe many moons of these outer planets formed. So in sister theory, it suggests that the moon was created along with our planet, but it was rejected because it could not define the speed of the moon. So the third theory is the capture theory, which states that the moon was formed elsewhere in the solar system and is captured by Earth. So it believes that the moon was wandering in space aimlessly, and when it came closer to the Earth, it was captured by the Earth's gravity, and that caused the moon to stuck in the gravitational field of our planet. But those 3 hypotheses that was presented about how the moon formed was all rejected because of the lack of evidences. So the easiest hypothesis to reject is the capture theory, because its primary drawback is that no one knows of any way that early Earth could have captured such a large moon from elsewhere. One body approaching another cannot go into orbit around it without a substantial loss of energy. This is the reason why the spacecraft destined to orbit other planets are equipped with retro rockets. And the second hypothesis that was rejected was the fission hypothesis, which states that the moon separated from Earth was suggested in the late 19th century. Modern calculations have shown that this sort of spontaneous fission or splitting is impossible. So furthermore, it is difficult to understand how a moon made out of terrestrial material in this way could have developed the many distinctive chemical differences now known to characterize our neighbor. And because the first 2 hypotheses was all rejected, the scientists were therefore left with the sister hypothesis, which states that the moon formed alongside Earth, or with some modification of fission hypothesis that can find a more acceptable way for the lunar material to have separated from Earth. But the more we learned about our moon, the less these old ideas seem to fit the bill. And because those 3 theories was all rejected, scientists now developed a 4th hypothesis, and they called it the giant impact hypothesis. So what is giant impact hypothesis? The giant impact hypothesis is the concrete and widely accepted theory on how the moon formed. There is also increasing evidences that large chunks of material, objects of essentially planetary mass, were orbiting in the inner solar system at the time that terrestrial planets formed. The giant impact hypothesis envisions Earth being struck obliquely by an object approximately 1/10 Earth's mass, a bullet about the size of Mars. So this is very nearly the largest impact Earth could experience without being shattered. Such an impact would disrupt much of Earth and eject a vast amount of material into space, releasing almost enough energy to break the planet apart. Computer simulation now indicate that material totaling several percent of Earth's mass could be ejected in such an impact. Most of this material would be from the stony mantle of Earth, and the impacting body not from their metal core. This ejected rock vapor then cooled and formed a ring of material orbiting Earth. And it was this ring that ultimately condensed into the moon. And to sum up the giant impact hypothesis, let me tell you a short story behind it. A million years ago, there is a planet about the size of Mars called Theia collided with our Earth. And when they collided with each other, due to heat explosion, they melted only to form a new giant body known today as our Earth. Only a small part of those two planets were collected near the Earth's orbit, which in time formed into the moon that started to revolve in our planet. And while we do not have any current way of showing that the giant impact hypothesis is the correct model of the moon's origin, it does offer potential solutions to most of the problems raised by the chemistry of the moon. So first, since the moon's raw material is derived from the mantles of the Earth and the projectile, the absence of metals is easily understood. Second is that most of the volatile elements would have been lost during the high temperature phase following the impact, explaining the lack of these materials on the moon. Yet, by making the moon primarily terrestrial mantle material, it is also possible to understand similarities such as identical abundances of various oxygen isotopes. Now let us explore the planet Mercury as one of the so-called the cratered worlds. So, let me present to you first the learning objectives. By the end of the section, you will be able to characterize the orbit of Mercury, describe Mercury's structure and composition, explain the relationship between Mercury's orbit and rotation, describe the topography and features of Mercury's surface, and summarize our ideas about the origin and revolution of Mercury. Let's discuss first the Mercury's orbit. So please keep in your mind that the planet Mercury is similar to the moon in many ways. Like the moon, it has no atmosphere and its surface is heavily cratered. So Mercury is the nearest planet to the sun, and in accordance with the Kepler's third law, it has the shortest period of revolution about the sun, 88 of our days, and the highest average orbital speed of 48 kilometers per second. It is appropriately named for the three-footed messenger god of the Romans. Because Mercury remains too close to the sun, it can be difficult to peek out in the sky. As you might expect, it's best seen when its eccentric orbit takes it as far from the sun as possible. The semi-major axis of Mercury's orbit, that is the planet's average distance from the sun, is 58 million kilometers or 0.39 AU. However, because its orbit has the high eccentricity of 0.206, Mercury's actual distance from the Sun varies from 46 million kilometers at perihelion to 70 million kilometers at aphelion. So when we say perihelion, it is the closest point of planet's orbit to the Sun, while aphelion pertains to the farthest point of planets to the Sun. So these ideas and terms that describe orbits were introduced in Orbits and Gravity. Now let's proceed to the composition and the structure of Mercury. So Mercury's mass is 1/8 that of Earth, making it the smallest terrestrial planet in our solar system, except of course for the dwarf planets. So having a diameter of 4,878 kilometers, less than half that of Earth. Mercury's density is 5.4 grams per centimeter cube, much greater than the density of the Moon, indicating that the composition of those two objects differs substantially. Mercury's composition is one of the most interesting things about it and makes it unique among the other planets. Mercury's high density tells us that it must be composed largely of heavier materials such as metals. The most likely models for Mercury's interior suggest a metallic iron nickel core amounting to 60% of the total mass, with the rest of the planet made up primarily of silicates. The core has a diameter of 3,500 kilometers and extends out to within 700 kilometers of the surface. So we could think of Mercury as a metal ball the size of the moon, surrounded by a rocky crust 700 kilometers thick. Unlike the moon, the planet Mercury does have a magnetic field. So as you can remember, one of the characteristics of moon has no magnetic field. So the existence of this field is consistent with the presence of a large metal core, and it suggests that at least part of the core must be liquid in order to generate the observed magnetic field. This figure presents the Mercury's internal structure. The interior of Mercury, as you can see, is dominated by a metallic core about the same size as our moon. We're done with the composition and the structure of Mercury, so let us now proceed to the Mercury's strange rotation. So, visual studies of Mercury's indistinct surface markings were once thought to indicate that the planet kept one face to the Sun, as the Moon does to Earth. Thus, for many years, it was widely believed that Mercury's rotation period was equal to its revolution period of 88 days, making one side perpetually hot while the other was always cold. Radar observations of Mercury in the mid-1960s, however, showed conclusively that Mercury does not keep one side fixed towards the Sun, for the reason that if a planet is turning, one side seems to be approaching Earth while the other is moving away from it. The resulting Doppler shift spreads or broadens the precise transmitted radar wave frequency into a range of frequencies in the reflected signal. The degree of broadening provides the exact measurement of the rotation rate of the planet. So we'll see its illustration to the next slide. This illustration shows the Doppler radar measures rotation. So as you can see, when a radar beam is reflected from a rotating planet, the motion of one side of the planet's disk toward us and the other side away from us causes Doppler shifts in the reflected signal. The effect is to cause both a red shift and a blue shift, widening the spread of frequency in the radio beam. Mercury's period of rotation, or how long it takes to turn with respect to the distant stars, is 59 days, which is just two-thirds of the planet's period of revolution. Subsequently, astronomers found out that a situation where the spin and the orbit of a planet, its sphere, are in a 2 to 3 ratio turns out to be stable. The planet Mercury, as being close to the Sun, is very hot on its daylight side. But because it has no appreciable atmosphere, it gets surprisingly cold during the long nights. The temperature on the surface climbs to 700 Kelvin or 430 degrees Celsius at noontime. After sunset, however, the temperature drops, reaching 100 Kelvin or 170 degrees Celsius just before dawn. It is even colder in craters near the poles that receive no sunlight at all. The range in temperature on Mercury is thus 600 Kelvin or 600 degrees Celsius, a greater difference than on any other planet. Now let's have some connections, what a difference a day makes. So, Mercury rotates 3 times for each 2 orbits around the Sun. It is the only planet that exhibits this relationship between its spin and its orbit, and there are some interesting consequences for any observers who might someday be stationed on the surface of Mercury. Here on Earth, we take for granted that days are much shorter than years. Therefore, the two astronomical ways of defining the local day, how long the planet takes to rotate and how long the Sun takes to return to the same position in the sky, are the same on Earth for most practical purposes. But this is not the case on Mercury, because while Mercury rotates or spins once in 59 Earth days, the same time for the Sun to return to the same place in Mercury's sky turns out to be 2 Mercury years or 176 Earth days. So as you can remember, a day in Mercury equals to 88 Earth days. Just imagine if one day at noon a Mercury explorer suggests to her companion that they should meet at noon the next day. This could mean a very long time period. Let's move on to the surface of Mercury. So the first close-up look at Mercury came in 1974 when the US spacecraft Mariner 10 passed 9,500 kilometers from the surface of the planet and transmitted more than 2,000 photographs to Earth, revealing details with the resolutions down to 150 meters. Subsequently, the planet was mapped in great detail by the Messenger spacecraft, which was launched in 2004 and made multiple flybys of Earth, Venus, and Mercury before settling into orbit around Mercury in 2011. It ended its life in 2015 when it was commanded to crash into the surface of the planet. Mercury's surface strongly resembles the Moon in appearance. It is also covered with thousands of craters and larger basins up to 1,300 kilometers in diameter. Some of the brighter craters are rayed like Tycho and Copernicus on the Moon, and many have central peaks. There are also scarps or cliffs more than a kilometer high and hundreds of kilometers long, as well as ridges and plains. Messenger instruments measure the surface composition and map past volcanic activity. One of its most important discoveries was the verification of water ice, first detected by radar, in crater near the poles, similar to the situation on the Moon, and the unexpected discovery of organic, carbon-rich compounds mixed with the water ice. Now let's proceed to these two illustrations. The first illustration is the largest known structural feature in Mercury. The smooth plains in the interior of the basin have an area almost 2 million square kilometers. So the second illustration from Messenger data, it is the topography of Mercury's northern hemisphere. The lowest regions are shown in purple and blue, and the highest regions are shown in red. The difference in elevation between the lowest and highest region shown here is roughly 10 kilometers. The permanently shadowed low-lying craters near the North Pole contain rather bright water ice. Most of the Mercurian features have been named in honor of artists, writers, composers, and other contributors to the scientists commemorated on the Moon. Among the named craters are Bach, Shakespeare, Tolstoy, Van Gogh, and Scott Joplin. There is no evidence of plate tectonics on Mercury. However, the planet's distinctive long scarps must have formed later than craters. As you can see in the illustration, these long, curved cliffs appears to have their origin in the slight compression of Mercury's crust. Now let's move on to the origin of Mercury. So the problem with understanding how Mercury formed is the reverse of the problem posed by the composition of the Moon. We have seen that, unlike the Moon, Mercury is composed mostly of metal. However, astronomers think that Mercury should have formed with roughly the same ratio of metal to silicate as that found on Earth or Venus. So how did it lose so much of its rocky material? The most probable explanation for Mercury's silicate loss may be similar to the explanation for the Moon's lack of metal core. Mercury is likely to have experienced several giant impacts very early in its youth, and one or more of these may have turned away a fraction of its mantle and crust, leaving a body dominated by its iron core.